Hello and welcome back to our video series. We are going to look at a new topic in this series, which is based on the power electronics. So what is really a power electronics? A power electronics is a branch in electrical engineering where we look at the electronics that controls the power. In a power generation and the transmission scheme, we are going to look at how the power is generated and how it is transmitted to the distribution end. So we normally have the source. We have the source that produces the energy, especially the electrical energy, and it is transmitted. And it is transmitted to the distribution. So the source is mostly generation, and the source, we know that we have the AC source and the DC source. And AC source is mostly generated from a generator, hydro, a wind turbine, and so on. However, for the DC source, it can be from a battery, a solar, or a DC bus. And all of these can be regarded as the generation side of the power system. And it is transmitted. So it is mostly transmitted using electrical cables, and most of these electrical cables can be a copper. A copper is known as a good conductor of electrical energy. And when we look at the distribution side, we have what is called the load, and this load can be, example, a fan, we have television, a mobile phone, or motor, and many other things that can use this particular electrical energy. So if we have a power plant, and this power plant is responsible for producing the AC, and it is transmitted to the electrical lines, and before it is connected to those lines, if the distance is great, then we have to boost. So if we have the power plant that produces 240 volts AC, it can go through a transformer and it can boost to 11,000 volts AC. And now it can be transmitted via the electrical cables. And those electrical cables can be seen by the poles that we normally have. And then before it reaches the distribution end, which is the load, especially a house or a industrial plant, then it must also go through another transformer. And this transformer is now reducing the 11,000 kilovolts AC to 240 volts AC, and then it is now connected to the load, and this load can be the house or any industrial plant. And we can see that the power plant produces the AC, and then this AC is now passed through a transformer. A transformer acts as an inductor, and it has the primary side and the secondary side. And the output is also AC, and this AC will now pass through the electrical lines and to another transformer. And this transformer will now also step down the high voltage into a low voltage, and it has a primary side with N1, which represent the number of turn of the coil, and we have N2, which represent the secondary side of the transformer. And now we have again our 240 volts AC, which can be used. If I have to discuss the transformer, for a step-up transformer, ideally we normally have the N1, which must be less than the N2, which represent the number of turns of the coil inside the transformer. And for the step-down transformer, we normally have the N1, which is greater than the N2. By looking at this diagram, those parameters that are involved, especially the voltage and the current, which is of great value. So we have high voltage and high current. And in order to control such high voltage and high current, we normally use the power electronics component. And this component that make up the power electronics can withstand this high voltage and high current within the power generation, power transmission, and the power distribution. And this is the basic understanding of why we need power electronics, because we are dealing with such high value of the parameters such as the voltage and the current, and not forgetting the frequency and the phase in an AC signal. Now we will dive into knowing what really makes power electronics very important in the power generation, transmission, and the distribution, and what are some of the circuits that involve in the conversion of such electrical energy. When describing the source, we said that we normally have the AC and the DC. So they become our primary or secondary sources. In order to control this type of primary and secondary sources, we need what is called the converters. And those converters are responsible for changing the properties of the signal itself. If we are to discuss those type of power electronics converter, we can clearly see that we have the power electronics converters. And these power electronics converters can be further broken down into AC to DC converters, and we have DC to DC converters, and we have DC to AC converters, and we have AC to AC converters. So those converters play a vital role in power system, especially power system generation, transmission, and distribution. And this can be the category of the converters that we will discuss. And there are circuits that involves as well as the name given to each of these power electronics converter. For example, for AC to DC, we normally call it as a rectifier. So a rectifier is a circuit that perform rectification, and rectification meaning that it will convert from AC to DC. So we have sources such as the AC source, it will convert to a DC source. And we have the diode rectifier, which is responsible to convert the AC to DC. And we have another one, which is the phase control rectifier. So these two is mostly used in the process of converting the AC signal to a DC signal. And we have a DC to DC converter, such as the buck converter and the boost converter. And to convert the DC to AC, we have the circuit which we all know, such as the inverter. So the inverter is responsible for converting a DC signal into the AC signal. And we have the AC to AC converter, which we normally call the cyclo converter. And we have the AC voltage regulation. And these two types of circuit normally convert an AC signal to an AC signal, but it will vary some of the components such as the phase, the voltage, and the frequency. And we will start our discussion by understanding what is a DC to DC converters. So imagine for a DC to DC converters, if we have a 12 volts DC and we want to limit the value to a lower value such as 5 volts. Now in this case we have a DC to DC converter known as the buck converter. And this buck converter is responsible for stepping down a higher voltage to a lower voltage. And if we have example 5 volts DC and we want to increase the voltage magnitude to a higher value such as 12 volts DC, now we normally use a boost converter. There are many designs that are used to integrate both the buck and the boost converter in an hybrid mode. So we normally have the buck boost converter, which is responsible for behaving like a buck by stepping down a voltage, or it can act as a boost converter by boosting the value of the voltage such as the 5 volts to a higher volts. And in this video we are going to look at the buck converter, and we will look at some of the operating mode and the circuit diagram and why we use buck converters in application such as charging a mobile phone, solar energy, power conversion, or different rating of power in an electrical circuit where we want to step down a voltage from some high value into a lower value, and it can be used in a DC component. And for the buck, imagine if we have a circuit board where the input to the circuit board is 9 volts, and we have some subsystem which uses different voltage level such as 6 volts, 5 volts, and 3 volts. In order to convert the 9 volts into the equivalent 6 volts, 5 volts, 3 volts, that means they have a lower value. A buck converter circuit is now responsible for converting this higher voltage such as a 9 volts into each of these voltage which is required by each of the subsystem inside a overall system. And we will also look at the important thing that control the entire operation of the buck control circuit in the power electronics. So the buck DC to DC converter, the main function is to step down higher input voltage to the output lower voltage. If we have a block diagram, we now can have the buck controller, which we have the lower output voltage, and we have the higher input voltage. If you are working on any circuit or any power electronic devices that requires a lower output voltage, then you will choose the buck converter, because the buck converter has the property or the ability to convert the higher input voltage into the lower output voltage. Now we can look at the circuit diagram, and I will explain how the circuit operates and how it steps down the higher voltage into a lower output voltage. So I will draw the circuit diagram as follows. Now we have the voltage input and we have a switch and we have a diode, we have the inductor, we have the capacitor, and we have the resistor load. And this is the switch, and this is the diode, and this is the inductor, this is the capacitor, and this is the resistor load. And this is a fundamental DC to DC buck converter circuit diagram. And I will briefly discuss the input and the output characteristic of a DC buck converter. And also I will discuss the derivation of this buck converter in terms of the state phase, average model, we normally call it SSA, which is the state space average model, and I will discuss the generalized state space average model, GSSA. And with this in mind, we are going to model the DC to DC buck converter by looking at the characteristics such as the voltage input. The voltage input will always be a DC voltage, and we normally have the switch, and this switch can be a MOSFET. We previously discussed what is a MOSFET. A MOSFET is a voltage control device, and to control we normally need the PWM signal, and PWM signal is the pulse width modulation signal. And we have the D, which is nothing but a diode, and we have the L, which is our inductor. And we know that for the diode, it only allows the flow of current in one direction only, and from the symbol that means in this direction. And we know that inductor is an electrical component that stores energy in its magnetic field. So we have the inductor, which is something like this, and because of the coil of the wires, it will produce a field, and this field is now responsible for storing the electrical energy, so in terms of its magnetic field. And we have a magnetic field and electric field. Electric field can be found in an atom, where we have the force that bonds the electrons of an atom with its nucleus, and this type of field is known as an electric field. However, in inductor like this, we normally have the magnetic field, and this magnetic field is responsible for storing the electrical energy. And we have a C, which represents the capacitor. So a capacitor is mostly used for storing the voltage, and this voltage can also be known as storing of the electrons. And finally, we have the RL, which represent our resistor load, and this resistor load is now having the ability to use up the electrical energy. So if you want to build a buck DC to DC converter, you should have all these electrical components available. One thing I want to explain is the PWM signal, because the PWM signal is now responsible for controlling the output to be lesser than the input. And this PWM signal is now called the control of the buck DC to DC converter. To differentiate between PWM and a DC voltage source, if we now have a DC voltage source and having a magnitude of 1 volts and to infinity, then this voltage is constant throughout. Now if we want to have a PWM signal, for this PWM signal we have a period that usually control the DC voltage source, and we can have a PWM signal drawn like this. And to fully understand, this portion is called the on state and this portion is called the off state. And we know that the frequency of a PWM signal, which is equals to 1 over the period. A period is a time taken to complete one full cycle. And from this graph, if we start from here and we end from here, now this becomes our period. And there is a difference between the period and the turn off and the turn on cycle of the PWM signal. And this can be T on and this can be the T off, where the turn on, which is also a period of the switching on of the PWM signal, having the value of 1, 0, 1, 0, 1, 0 and so on. And the turn off time, which represents the period in which the signal is switched off, which is represented by the 0. In this case, we are talking about 3 different periods. One is the period for the turn on time, 2 is the period of the turn off time, and we have the period which represent a complete cycle from turn on to turn off. So this can be regarded as a period of one cycle where we have on and off. And I want you to fully understand the PWM signal, because this PWM signal will be the control of the converters. Without this PWM signal, we cannot be able to convert a voltage of higher magnitude into a voltage of lower magnitude. And if we now discuss the PWM signal, we have the duty cycle, and we have the duty cycle which range from 0 to 1. And this duty cycle is now responsible for varying the turn off and the turn on period of the PWM signal. If we have a duty cycle of 0.5, now we will have the period for the turn off time, which will be 0.5, and for the turn off we will have 0.5. And now both will gives us a value of 1 complete cycle, because this will be having a period which is 0.5, and this will also have a period of 0.5. And now the frequency is set between the period of the turn on and the period of the turn off cycle of the PWM signal. I will draw a magnifying PWM signal so you can be able to see clearly. So if we have the 0.5, that means this will be the half, which represent 0.5 cycle, and this will represent 0.5 cycle. So the T on is 0.5 and T off, which is equals to 0.5, and we can have the period for both will be equals to 1, and in that case we normally have 1 which represent the time. So for a 1 second cycle, that means we can have period equals to 1 over 1 second. We now have the frequency, which is 1 cycle per second, and that means this one we have a half cycle, and for the 10 off we have another half cycle. So both of these 10 on and 10 off, they form the 1 cycle, and the time is 0.5 seconds, which is set between each of these 10 on and 10 off cycle. So the total period in a PWM signal will be this portion for 10 on and 10 off, which can be regarded as a fundamental frequency of the PWM signal. However, 10 on is the time taken for the wave to 10 on from 0 to 1 all the way to 0.5 seconds, and 10 off is the time taken when the waveform is from 1 to 0. So we have this represent the 10 off because this wave has been 10 off, and when it is 10 on we have this wave given here. And in this case, where let's say if we have 0.8, which is our duty cycle, so what does that really mean? So we can have the T on, which is now becomes 0.8, and the 10 off will now be equals to 0.2, and 0.8 and 0.2 will give the fundamental period, which is equals to 1, and it represents also 1 cycle of the wave in terms of the 10 on and the 10 off. And if we are to draw the magnifying wave, we can now be able to see if this is 0, 0.5 and we have 1, we now should move to 80. So we can have 5, 6, 7, 8. So this can be the region of 0.8. So if we have 1 here, now the 10 on will be 80% the duty cycle. So we can say this is 0.8 and the off is only 20%. So this represents 80% of 10 on and 0.2, which can represent 20% of the 10 off. So in this case, you can see that the period for both the 10 on and 10 off changed. However, the period of the waveform is still constant. Imagine if we change the frequency of the PWM signal. Now it will affect the fundamental period of the waveform. However, the 10 on and the 10 off will vary based on the duty cycle. And now this duty cycle is responsible for controlling the PWM signal. And in that case, it will control the 10 off and the 10 on period of the PWM signal, which is known as the pulse width modulation signal. And since it has a pulse, that means we have this represent the pulse train wave. And when we talk about the width, we are talking about the width of the 10 on. This is the width of the 10 on and this is the width of the 10 off. That is why it is called a pulse width modulation signal. So in other words, if the 10 on is, let's say, we have the duty cycle, as 0.1. Now we can see from this waveform, and we can see the period of the 10 on, which will be equals to 0.1 seconds, and for the 10 off which can be 0.9 seconds. And if we have 0.5 and 1 here, and we have the amplitude of 1, we can see that this should be the 10 on, and from this region, which is the 10 off. So the waveform should be like this, and if it is continuous, then we should have something like this, and something like this, and so on. So this represents the duty cycle, which is 0.1 in decimal, or we call it 10% duty cycle. In this case, we have the representation of the duty cycle as 0.8 in percentage. It is 80% duty cycle. So this duty cycle is responsible for controlling the 10 on time of the PWM signal. The easiest way to calculate the duty cycle, which is D, is by having the magnitude of the voltage output divided by the voltage input. In this equation, you can be able to find the duty cycle of the DC-DC buck converter. Imagine if we have 12 volts input and we want to get a 5 volts output to control some electrical device. Now, the duty cycle can be calculated such as 5 divided by 12. When 5 divided by 12, we should get around 0.42. So now 0.42 is now our duty cycle. So we can have the duty cycle which controls the PWM signal, which is now our control signal that will be applied to the switch. And this switch will now be able to manage the 12 volts to have a 5 volts at the output. So these are the basic characteristic and the operation of a DC to DC buck converters. So in our next video, we will discuss some mathematical equation for the state-based modeling and the generalized state-based modeling of the DC to DC buck converter, and we will see what is really happening in the DC to DC buck converters and how can we achieve a lower output voltage from a higher input voltage. Thank you for watching our video. Kindly subscribe to our channel and share this video with your friends so they can also be able to learn.